Picture a catastrophic industrial failure, like a massive rotating machine housed inside this really heavy steel casing, and it has just been completely
Oh,
destroyed.
yeah, it's an absolute mess.
Right. We're looking at a specific image right now, courtesy of the Bentley Nevada Corporation, and it shows this giant rotor that has literally blown itself apart.
It's terrifying, honestly.
The heavy metal housing is shredded, solid steel pipes are twisted like, I don't know, wet spaghetti, and it looks for all the world like a bomb went off inside this factory.
Yeah.
But there was no explosive, there was no fire. The machine was destroyed entirely by its own excessive vibrations.
It really is a terrifying image, and it perfectly sets the stakes for what we're exploring today.
Welcome to the deep dive. Our mission today is a bit of a, I guess, a translation exercise. We're taking a stack of mechanical engineering lecture notes and, turning them into a gripping, digestible format. We are breaking down the core concepts of mechanical vibrations. So whether you are an undergraduate engineering student trying to wrap your head around complex dynamics, or you're just insanely curious about how the massive machines all around us work.
Or how they break.
Right, and more importantly, how they violently break. You are in the exact right place.
And we really have to extend a huge thank you to Dr. Chandan Chattoraj. He shared his ME 503 lecture notes with us, and those notes form the entire foundation of our conversation today.
Yes, absolute goldmine of information.
It really is. It's essentially a masterclass in why things shake, rattle, and eventually explode.
Absolutely. Thank you, Dr. Chattoraj. Now, before we can understand how a solid steel machine tears itself apart, we need to quickly align on the language of vibration.
Right, the basics.
Yeah, I promise we won't drag you through basic physics. We know what speed and acceleration are, but the notes highlight a few specific vibration terms we need to lock in. Okay, let's unpack this. Think of this as your conceptual glossary.
Yeah.
First, time period. That's just the time it takes in seconds for one complete cycle of a vibration to happen. And a cycle is that one complete sequence of movement, say, swinging all the way forward, all the way back, and returning to the center.
Right. And frequency is simply how many of those complete cycles happen in a single second, which we measure in hertz.
Okay, hertz, got it.
Though because engineers are usually dealing with spinning shafts and rotors, they often use circular frequency, which actually measures the rotation speed, usually in radians per second.
Exactly. Then we have amplitude. This one is crucial. Amplitude is the maximum distance the vibrating body moves from its resting position.
Yeah, how far it actually travels.
Right. It's how far the machine is physically bending or stretching during the shake. And finally, response. In engineering, response is the overall physical behavior of the system when it's subjected to an outside force. Like, how does the machine react when something pushes it?
And that concept of the push is where things get interesting and, well, often where things get incredibly dangerous.
Which brings us right to the root of the problem. Before a machine ends up looking like that blown-apart rotor in the photo, what actually starts the shaking?
Right. The root cause.
Because a perfectly designed, perfectly balanced machine shouldn't vibrate at all, right?
I mean, in a flawless theoretical universe, no. But the real world is messy. The notes break down the root causes of vibration into three main categories. You've got repeating forces, looseness in the assembly, and resonance.
Okay, let's unpack that first one. Repeating forces. What does that actually look like inside a machine?
Well, a great example from the notes is found inside an everyday electric motor. So inside a motor, you have a spinning center, the rotor, surrounded by a stationary part, the stator.
Right.
And there's this tiny air gap between them. Now, what happens if that air gap isn't perfectly equal all the way around?
Oh, I'm guessing the magnetic pole gets lopsided?
Precisely. You generate an unbalanced magnetic force. As the motor spins, the strongest point of that magnetic pole rotates with it. Yeah, it creates a repeating invisible force that continually yanks the motor off its center axis over and over again.
That makes perfect physical sense. It's an invisible force, pulling unevenly. What else causes this?
Simple friction is a huge culprit here. The notes use a brilliant non-industrial analogy to explain this. A violin.
A violin.
Yeah, think about how a violin string works. The friction between the bow and the string grips the string, pulls it slightly, and then the string slips back. Grip, slip, grip, slip.
Oh, I see.
That alternating friction is what causes the string to vibrate and actually create sound.
Oh, wow. So in a massive factory machine, if you have two components rubbing against each other without enough lubrication, that same grip and slip friction can cause a solid piece of steel to vibrate like a giant violin string.
Exactly. And the energy involved is massive. You also have impact forces, Like, imagine gear teeth grinding against each other.
Ow.
Or think of a tiny flaw in a bearing raceway. Every time a steel ball bearing rolls over that microscopic dent, it's like a car hitting a pothole at highway speeds.
Oh,
Yeah.
man.
It just sends a massive shockwave right through the machine.
So engineers are dealing with magnetic pulls, friction, and internal potholes. But because these forces are mostly invisible or hidden deep inside the metal casing, how do engineers actually map them out to understand them?
So they use a mathematical model called a harmonic forcing function.
Okay.
Don't worry, we aren't going to read out giant equations here. Conceptually, think of this function as drawing a perfect, repeating ocean wave on a graph. This wave visually represents the invisible force pushing on the machine.
Right. And to draw that wave, engineers need to know three specific things, which make up the variables in their equations. First, they need the amplitude, which basically tells us how tall the wave is or, how hard the force is physically pushing. Second, they need the frequency, how close together the waves are, meaning how often the push is happening.
Right. And the third piece is the phase angle.
Yeah.
This one is a bit more abstract, but think of it as a timing delay. Yeah. If the force pushes the machine right now, how long does it take for the machine to actually physically move in response? The phase angle represents where the wave starts its cycle relative to the machine's actual movement.
Okay, that makes sense for moving parts. But I'm looking at Dr. Chattoraj's notes here, and I want to push back on something. Everything we've discussed so far, motors, gears, bearings, is highly mechanical and involves spinning parts. Does this harmonic wave stuff only apply to active machinery? Like, what about stationary structures?
What's fascinating here is that stationary objects are absolutely vulnerable to these exact same harmonic forces, usually generated by their environment. The notes highlight a really cool phenomenon called vortex-induced vibration.
Vortex-induced vibration, how does that work?
Imagine a tall, slender, stationary structure. A factory chimney is a perfect example. When wind blows across that cylindrical chimney, the air doesn't just flow smoothly around it.
Right, it hits it and scatters.
Yeah, as the wind splits and goes around the sides, it creates swirling pockets of low-pressure vortices behind the chimney. But they don't form evenly. They detach or shed, alternating from the left side, then the right side, then the left side.
Oh, so because they are low-pressure pockets, they are literally creating a vacuum that sucks the chimney to the left, then to the right, then to the left.
Yes, that alternating pressure drop acts exactly like the harmonic wave we just talked about. The wind is effectively plucking the giant steel chimney side to side.
That is wild to visualize. The wind is playing the chimney like a guitar string.
All right, so we know what these forces look like, whether it's a magnetic imbalance or the wind. But let's get back to the machinery. How do these forces physically destroy a heavy, solid steel shaft, like the one in that Bentley, Nevada photo?
This takes us into the highly dangerous territory of shaft whirling.
Whirling. Sounds bad.
It is. To understand whirling, you have to realize that a rotating shaft rarely sits inside a machine naked. It carries heavy mountings, gears, pulleys, massive metal discs. Now, ideally, when you build this, the center of gravity of that heavy gear aligns perfectly with the exact center axis of the shaft.
But as we established, the real world is messy. Ideal doesn't happen often on a factory floor.
Rarely.
Yeah.
Due to slight design asymmetries or just a tiny misalignment error during assembly, the center of gravity of that heavy gear is almost always slightly off-center from the axis of rotation.
Okay, I think I see where this is going. As the shaft spins, that heavy off-center weight starts pulling outward, like being pushed against the door of a car taking a sharp turn.
Exactly. It is subjected to centrifugal force. And because the shaft is made of metal, which has some flex to it, this pulling force literally bends the solid steel shaft slightly outward.
But wait, if the shaft bends outward, doesn't that move the heavy center of gravity even further away from the center axis?
Yes. And that right there is the terrifying cumulative feedback loop that destroys machines. The bending moves the center of gravity further out. A larger radius creates a stronger centrifugal force. That stronger force bends the shaft even more, which moves the weight out further, increasing the force again. It is a vicious runaway cycle.
And as it bends and spins, the whole bent shape is whipping around the center axis. Like, imagine swinging a heavy bucket full of water on a stretchy bungee cord.
Oh, that's a great visual.
The faster you spin in a circle, the heavier the bucket feels, and the more the bungee cord stretches. The faster you go, the further it pulls away from you.
That is a perfect physical analogy for what the notes call synchronous whirl. But here's where it gets deadly. Every physical system has a natural frequency. the specific speed it naturally wants to vibrate at, determined by its mass and how stiff it is. Now, what happens when the speed you are spinning the shaft exactly matches that natural frequency?
You hit the ultimate danger zone.
You hit what engineers call critical speed. At this exact speed, the system goes into resonance. Mathematically speaking, the equations state that the additional deflection of the shaft becomes infinite.
Okay, hold on. I have to call a timeout here. Infinite deflection. That's physically impossible. A steel shaft cannot stretch to infinity. It would break first.
You are absolutely right. The math equation produces infinity because a theoretical model assumes the material can stretch forever without breaking.
Right. Math doesn't care about real steel.
Exactly. In physical reality, infinity means the centrifugal force violently overcomes the restoring stiffness of the steel. The shaft bends until it snaps, or until it physically shreds the casing around it. That Bentley, Nevada photo, that is what infinity looks like in the real world.
Okay, that is a terrifying clarification. So what is the practical safety tip here for an engineering student? Just never, ever spin a machine at that critical speed.
That is the primary rule. Avoid that speed range entirely. However, the notes point out a practical reality. Many modern machines, like high-performance turbines, operate at a normal speed that is actually above their critical speed.
Wait, really?
Yeah, meaning every time you turn them on, they have to pass through the danger zone to get to their safe operating speed.
Oh, man. So how do they survive starting up?
The operational rule is transition through the critical speed zone instantaneously. Do not linger. You literally punch the throttle and accelerate past it so quickly that the vibration doesn't have enough time to build up that catastrophic cumulative feedback loop.
Get through the danger zone before the bungee cord has time to snap. Got it. But if the theoretical math says the bending goes to infinity right at that critical speed, how do engineers actually calculate the machine's behavior as it gets closer and closer to that breaking point?
To map that out, the notes introduce a crucial concept called the frequency ratio. It's a very simple relationship. It is the speed the machine is currently running at, divided by the natural critical speed it wants to vibrate at.
Okay, so if the ratio is exactly 1, you are at critical speed.
Exactly. And Dr. Chattoraj's notes break down the physical response of the system into 3 distinct physical cases based on this ratio.
Let's walk through these because the physics of what's happening inside the machine at these different stages is fascinating. Case 1 is when the ratio is much less than 1. So the machine is spinning relatively slowly. In this case, the pushing force of the imbalance is basically just arm wrestling the stiffness of the solid steel shaft.
Right. If we go back to our phase angle, that timing delay between the push and the movement, at low speeds, the delay is very small. The machine moves almost exactly when the course pushes it.
It's like pushing a kid on a heavy playground swing very slowly. You push, the swing moves with you. But then we speed up to case 2, the ratio equals exactly 1. We are at critical speed, resonance.
And something entirely counterintuitive happens to the internal forces here.
Yes. The phase angle, that timing delay, shifts to exactly 90 degrees. Can you explain why that happens physically? Like, what does a 90-degree shift actually mean?
Think back to your swing analogy. Imagine the kid is swinging back and forth. If you push them exactly when they are at the very bottom of the arc, when they are moving the fastest, you're pushing 90 degrees out of phase with the limits of their swing.
Oh, I see.
At this exact moment, the swing's momentum, its mass, and the gravity pulling it back, its stiffness, are perfectly balanced and they cancel each other out.
So your push isn't fighting gravity or the weight of the kid anymore.
Exactly. Your push is now entirely fighting just the air resistance and the friction in the chains. In a machine, at critical speed, the massive inertia of the spinning disc is perfectly canceled out by the spring stiffness of the shaft.
Oh, wow.
The exciting force is now entirely unopposed, fighting only the damping force, which is the internal friction of the system.
Which is why the vibration violently spikes. There's nothing left to hold the force back except friction.
Exactly.
And then we have case 3. We've punched the throttle and survived passing through critical speed. Now the ratio is much greater than 1. We are at extremely high speeds. Here, the phase angle delay approaches 180 degrees.
Meaning the push is happening completely opposite to the movement. At these hyper speeds, the stiffness of the shaft becomes almost irrelevant. The exciting force is almost entirely fighting the sheer inertia of the massive spinning weight.
Okay, here is where it gets really interesting. We have this mental image of a curve on a graph. The vibration amplitude gets bigger and bigger as we approach that ratio of 1, resonance.
Right.
But the notes detail the derivation for finding the absolute maximum amplitude, and the conclusion is a massive aha moment. Can you like translate the math of that step-by-step derivation for us?
I can, and it's a beautiful piece of physical logic. If you look at the master formula for how much a vibration gets magnified, you'll find the value for damping sitting right there in the denominator of the fraction.
Okay, and just basic fraction rules. To get the biggest possible result overall, you need the number on the bottom, the denominator, to be as small as possible.
Exactly. So engineers use calculus to find the absolute minimum point of that bottom equation. They want to find out exactly what speed ratio creates the perfect storm for maximum vibration. But when they solve for that lowest point, they discover something wild.
What is it?
Because damping acts as a mathematical drag in the equation, the result shows that the absolute maximum amplitude does not happen exactly at a speed ratio of 1.
It happens before 1.
Yes. When friction or damping is present in a system, the absolute worst, most violent shaking happens slightly before the machine hits its true natural resonance.
Why does that happen physically? I understand the calculus shows it, but what is physically happening inside the machine?
Think about what damping really is. It's friction, it's drag. That drag creates a slight sluggishness in the system's reaction time. So for the pushing force to perfectly align with the machine's movement to create that worst-case scenario, it actually has to hit just a hair early to overcome that sluggish drag.
Oh, that makes so much sense.
Yeah, the heavier the damping, the earlier that maximum vibration hits.
That is incredible. The perfect storm actually hits early because the machine is dragging its feet. That has massive real-world implications for a factory operator watching a vibration dial. They might think they haven't hit the worst of it yet, but they're already past the peak.
Exactly. It's super counterintuitive.
Okay, so all of this calculus gives us perfect curves on paper. We can calculate exact natural speeds. But how does this actually play out when maintenance engineers try to model and fix a real-world, rusty, greasy machine on a factory floor?
The notes have a fantastic section dedicated to this transition from theory to practice,
Mm.
mostly because they admit a hard, truth-perfect mathematical modeling is an illusion.
Really? Why is it so impossible to model?
Well, let's just look at mass. In our equations, mass is just a static number. A 100-kilogram rotor is 100 kilograms. But what if you are an engineer designing a ship? When a ship's massive hull vibrates in the ocean, it doesn't just vibrate its own steel, it physically drags a massive envelope of the surrounding ocean water back and forth with it.
Oh, wow. I never even considered that. You're physically dragging the ocean.
It's called hydrodynamic mass. How much water mass participates in the vibration? It constantly changes. Or think about a liquid tanker truck driving down a bumpy highway. The road causes vibration, but the liquid inside is sloshing around.
Right, the weight is shifting.
The mass is dynamically moving, changing the physics of the vehicle second by second. Exactly modeling the mass of a sloshing fluid is incredibly difficult.
And if just figuring out the mass is that hard, I imagine modeling the damping, the friction, is an absolute nightmare.
Damping is notoriously the hardest variable to pin down. The clean single number we use in equations is a gross simplification. In a real machine, damping is a chaotic, messy combination of several distinct physical phenomena all happening once.
Can you break those phenomena down? What kind of friction are we talking about?
Sure, first you have viscous damping.
Uh-huh.
Think of the fluid inside a car's shock absorber. The thick oil resists movement. Then you have coulombic damping. This is dry, contact friction. Imagine sliding a heavy, unlubricated wooden box across a concrete floor. That scraping resistance in a machine that's two dry metal surfaces rubbing together.
And the notes mention a third one, material hysteresis. What is hysteresis?
It is internal friction within the metal itself. Think of a metal paperclip. If you bend it back and forth rapidly, what happens?
It gets really hot right at the bend before it snaps.
Exactly. That heat is the internal crystalline lattice of the metal grinding against itself and dissipating energy. That is hysteresis. So you have fluids squishing, dry parts scraping, and the internal metal heating up, all at the exact same time. Accurately putting a single mathematical number on that total chaotic dissipation is a monumental task.
So how do engineers cope? They can't just throw up their hands and say it's too hard to build the machine.
They cope by using simplified models, classifying them by what they call degrees of freedom. A degree of freedom is simply the minimum number of independent coordinates you need to completely track the position of the system.
Right, so a simple weight bouncing on a single spring is a single degree of freedom. You just need one coordinate to track the weight up and down.
Exactly. And the notes give a very relatable automotive example. If you are designing a car suspension, a full car is incredibly complex. So engineers use a quarter car model.
The quarter car?
Yeah, they pretend the car is just one wheel and the suspension directly above it. The heavy axle is one mass, and the car body above the shock absorber is a second mass. Because you only need two coordinates to track those two masses, it is a 2 degree of freedom system.
Much easier to calculate. Or they can upgrade to a half-car model, mapping the front and back wheels on one side, which gives you 4 degrees of freedom.
Right. They simplify the math until it's workable. But even then, because the theory relies on so many assumptions about mass and damping, theoretical modeling is never enough to keep a real factory safe.
Which brings us to the diagnostics. If the math on paper is always a little bit wrong, how do maintenance teams diagnose a failing machine on site before the rotor blows up like our photo?
Because they can't perfectly calculate it beforehand, they have to meticulously measure the reality while the machine is running. The notes outline the 3 main types of diagnostic vibration sensors used in the field.
Let's walk through the toolkit.
First, you have displacement transducers. A common type is an eddy current probe. These sensors measure the physical distance the shaft is moving. Like how far is it physically bending off its center axis?
So they are measuring the actual amplitude we defined earlier.
Yes. Then you have velocimeters. As the name suggests, they don't care about the distance, they measure the speed of the vibration. How fast is that bent shaft whipping back and forth?
And the third sensor?
Accelerometers. These are extremely common. They measure how violently the speed of the vibration is changing, the physical g-forces of the shake. By securely mounting a combination of these 3 sensors on the casing of a running machine, engineers can essentially reverse engineer the math.
Oh, I see. They look at the real-world displacement, the actual velocity, and the true acceleration, and they plug those real numbers back into the equations to figure out what the true messy mass, stiffness, and damping of their system actually are.
Precisely. They let the machine tell them the math, instead of blindly trusting the math they used to build the machine.
That is brilliant. All right, we have covered a massive amount of ground today, from the invisible magnetic forces that start a vibration, to the runaway feedback loop of shaft whirling, to how engineers measure it all in the dirt and noise of a real factory. Let's see how much of this intuition stuck. It is time for a quick pop quiz for you, the listener. Just 2 questions based on the physics we just unpacked.
Oh, this is the ultimate test of the deep dive. Let's do it.
Question 1. If you have a machine rotor with a heavy unbalance, what happens to the centrifugal force as the bending of the solid steel shaft increases? Does the force decrease, stay the same, or increase?
Think back to the heavy bucket on the stretchy bungee cord.
The answer is it increases. It acts cumulatively. More bending means the heavy center of gravity moves further out. A larger radius creates more centrifugal force, which causes even more bending, the runaway loop.
Spot on. Okay, question 2. In a real-world system that has damping like friction or fluid drag, does the maximum, most violent amplitude of vibration occur exactly at resonance, after resonance, or before resonance?
Ah, the counterintuitive calculus moment. The answer is before it. Because damping creates a sluggish drag on the system's reaction time, the perfect storm of forces actually aligns to create the peak amplitude just slightly before you hit the true theoretical natural frequency.
If you got both of those right, you have an excellent physical intuition for ME 503.
So what does this all mean? Why dedicate a whole deep dive to phase angles and whirling shafts? Because whether you are designing the smooth suspension for the next generation of electric vehicles, engineering a massive skyscraper that won't sway when hurricane vortices shut off of it, or, just trying to keep a simple water pump from shaking itself to pieces in your basement, understanding vibration is everything.
It really is.
It is the literal difference between a highly functional piece of engineering and a pile of very expensive, very dangerous, twisted metal.
We spend an enormous amount of engineering effort, countless hours, and billions of dollars trying to avoid resonance. We build shock absorbers to damp it out, and we design heavy casings to stop machines from tearing themselves apart.
Yeah, fighting the vibration.
But I want to leave you with a final thought to ponder. Resonance isn't inherently evil. It is just an amplifier. It is the exact same physical mechanism that allows the hollow body of an acoustic guitar to project a beautiful chord across a room, or a tiny radio antenna to pull one specific invisible frequency out of thin air and turn it into music.
It's just a raw multiplication of energy.
Exactly. So here is the thought. As humanity constantly looks for new, clean ways to generate power, could the very destructive forces that we've spent centuries trying to stop, could they be intentionally harnessed?
Like on purpose?
Yeah. Could we build highly efficient energy harvesting systems that deliberately use vortex shedding and runaway resonance to generate electricity from the ambient, everyday vibrations of the world around us?
From total destruction to infinite creation, taking the force that blows apart a rotor and using it to light a city, that is definitely something to chew on. Thanks for joining us on this deep dive into Dr. Chattoraj's notes. We will catch you next time.